on our organic chemistry asynchronous classes. So you might access these at different times. We are now on the stability of cycloalkenes, so we will just focus on concepts. So for chapter 4 or LP4, you have the stability of cycloalkenes discussed. Why? Because that's how we know them. Stability is somewhat if that compound is not stable. So basically, it might pose danger to us, or it might be lost after a couple of hours. So if we're concerned about the compound, so we have to know these things. So that is stability. So now, since we are on cycloalkanes, stability is being discussed and how it was discovered and probably how unstable are there or stable or unstable. So first is it is titled ring strain. So they already know the strain on the angle. If you can see at the um, angles with respect to, because we know that cycloalkanes are single bonds, and if they are close, the open chain, of course, the open chain are single bond, and we know that those angles are 109.5 ideally. So we already have strain angles when we have steric strains. For example, you have a big group that is attached to that single bond, so it somehow shifted from that 109.5 degrees, and that shifting actually causes somewhat strain. So actually, if what causes strain is about the groupings. We call it actually, I think it is called steric strain and a combination of strain. But for this one, angle strain is the effect of that steric strain. You also have that probably the contortion of angle because you are closing the supposedly open chain carbon chains. Okay, so for it is being discussed here that if you have a smaller, actually there's a chemist here because one of the things that they found out, if I paraphrase this one, cycloalkanes, smaller cycloalkanes are not usually found in nature because they can attest that it has number of carbons here, it has number of hydrogens there, and then you have a single bond here. So they can really attest it that is a cyclo, and they have found out that most of the compounds cyclo is not on the smaller side. So there's a proposal actually that because your smaller compounds has bigger strain issues. Strain issues. That's what being discussed here. So angles are being measured, and then from those angles, the bond angles actually, or probably the energy of that whole molecule is being computed. I mean, so this is a graph that shows that. So this is cyclostrain energies, cycloalkane strain energies. So what they did is calculated by taking. Usually, this can be calculated by taking the difference between a cycloalkane heat of combustion, because alkanes can be, see, there's an application of it, because alkanes can be uh, reacted with oxygen in air, that is combustion, or probably oxygen in a closed space, just like the setup for measuring the enthalpy, the energy associated with it, enthalpies of combustion, usually in a closed chamber, so that all energies can be accounted for. So this is how they do it. Taking the difference between a cycloalkane heat combustion per CH2. So every cycloalkane versus how many CH2s. Because we know that what we'll have is CH2s because you're already attaching carbon to carbon, so there are already two bonds for that. You only have an available of two bonds for hydrogen. So that's why for a cycloalkane, they know that what is attached to that carbon are the CH2. So that's why they have just to compare it, the number of carbons actually with respect to the H2. As long as there is no other compound, so it is a good it's a good basis for comparison. So they compare the heat of combustion per CH2. So ibig sabihin, this is for 3 carbon. Ring size is 3, meaning there are 3 carbons, 4 carbons, 5 carbons. and as you can see, there is no strain in 6 carbons, and 7 carbons are another strain is another present. So by taking the graph of that one, the strain with respect to compounds, cycloalkanes. So these are the graph showing that there is strain actually. With smaller ones, there are actually strains after 7, but after 14, 15, 16, those cyclocompounds are not already strained. So meaning the first proposal, the scientist who was described on the upper side actually is somewhat correct, that the bigger the molecule is, the smaller the strain. So that's why all they can see is bigger size cycloalkane molecules, because they are not strained, meaning they are stable. But he is not totally right. Why? Because as you can see here, the carbon 6 has no strain. And after 14 actually has no strain. So those are the things that he is correct. There is no strain. That's why it is stable. Actually, there are a lot of cyclohexane, usually the 6 carbon, cyclohexane, that can be found in nature, meaning naturally it is being created by nature because it's stable. But as you can see here, there is a reason why the 7, 8, 9, and 10 is also somewhat not stable. But you can see that there is a pattern. The ring size 9 has the highest. Of course, the 3, 4 has the highest, but it drops to the 7, 8, 9, and 11. And of course, some of the reasons are really here. So the data field shows Bayer theory is only partially correct. Cyclopropane, cyclopentane, and did strain just as predicted, but cyclopentane is more strained than predicted. So from prediction, actually, they will see that this graph is just going down. But as you can see, the 6 is now not strained while the 5 is more strained. So from that prediction, your 6 should be more strained than this. So that's what it states here, according to the other the other theory. So from this is from experiment. It is shown that cyclopropane it is strained just but cyclopentane is more strained than predicted. So from prediction of what do you call this? Cyclohexane, cyclopentane and cyclohexane, they are not what is predicted. So prediction versus real stuff. So they have to come up with a discussion. Of course, they have to sort it out. What happens? The Bayes theory is wrong for the simple reasons that he assumed all cycloalkanes are flat. So first, that's why it is what was drawn there, the triangle, the quadrilateral, because they assume that those are in a perfect flat surface. Okay? Because that's how we view them at first. For us not to be, for us not to complicate things. So as simple as that, because they cannot understand yet the whole molecular concept. Again, stereochemistry is just being introduced in this time, 18 something. So they are not flat. So if they are not flat, the fact that the primary bonds, the single bonds, will now have a 109.5, and the bigger molecules can contort with that 109.5 somewhat closer, therefore the strain becomes lesser and lesser as bigger molecules comes in, but special cases on the hex side. So there is actually a reason for that. In fact, as we'll see in the next section, most cycloalkanes are not flat. They adopt the Packard three-dimensional. Packard meaning alternating or somewhat protruding Packard three-dimensional conformations that allow band angles to be nearly tetrahedral. So that tetrahedral is 109.5. As a result, angle strain, cha-cha-cha, blah, blah, blah. So after that, we know that there are strains like torsional strain. Torsional strain, there are meaning of this one. Angle strain, of course, the first plot that they have plot because it is not under 109.5, meaning the angle must contort. So we call that angle strain, the stress or the strain from the stress of contorting to that angle because it should close because of a cyclo. Torsional strain now is because there is a twisting on that angle, not on the stable form, so you have a torsional strain, the twisting. And then you have steric strain. of course, when you have bigger groups on other molecules probably that comes near to it, there is a stress on that creating a strain. Okay, so those are angle strain, torsional strain, steric strain. And then you have LO, probably will not be doing that. And then they discusses one by one. So how is it